Hi guys, good morning. Hope you're all ready. Shall we start?
Yes, sir.
Yeah, good. So we have started the new chapter, right? So we started with thermodynamics, right? So we saw the introduction, right? So we saw what do you mean by systems, surroundings, and boundaries, right? Then we went on to see what are the different types of systems. What are the 4 different types of systems? People, what are the 4 different types of systems?
Open system,
Hmm.
closed system,
Hmm.
adiabatic system,
Hmm. And anybody else? Isolated system, right? Okay. So in all these things, we know what is going to change, what is not going to change. It's going to be based on only 2 things: whether mass transfer is happening or whether heat transfer is happening, right? So in an open system, both will happen. In a closed system, heat transfer will happen, mass transfer will not happen. And within a isolated system, nothing will happen. No mass transfer, no heat transfer. And adiabatic system, no heat transfer, but mass transfer can happen, right? Okay. Then so we understood what systems are, what are the different types of systems. Then we went on to see how to describe a system. In the sense, how do you want to study about a system, right? So we went on to see the properties. So the thing which are going to be used to describe a system is what are going to be called as properties of a system, right? So there are going to be 2 types of properties: intensive and extensive properties. I know intensive properties are independent of the amount of substance present in the system, and extensive properties are going to be dependent on the amount of system. We gave examples for that, and I told you thermodynamics is a very useful tool. It is going to take very less information, but the amount of information it is going to give you is enormous. How is it going to take only less information? If you want to know anything and everything about the system, 100% description, right? So for that, I require just 3 things: 2 intensive properties and the number of moles. And I told you every time intensive properties will not be given. Sometimes extensive properties can also be given, but you can convert an extensive property into an intensive property by dividing the extensive property by the number of moles. Say, for example, volume. When I divide it by the number of moles, becomes molar volume. That becomes an intensive property. Same goes with energy: kilojoules, kilojoules per mole. So all these things, I'll be able to convert extensive property into intensive property. Okay. So then we went on to see how heat, right, and temperature are related, right? So I told you Q is directly proportional, Q's amount of heat, right? So Q is directly proportional to delta T, that is change in temperature. So we put a constant there, and that constant is what is called as, what is the constant called as?
Heat capacity.
heat capacity.
Good, right? So it is called heat capacity, right? And since our heat is an extensive property, it is going to depend upon the amount of substance present. So depending on what is the amount which I'm going to use, that is either I can use mass or number of moles. Accordingly, the name of the heat capacity will change. That is when I have mass heat capacity, and or something I have called as molar heat capacity, right? So we even went on to define what is heat capacity. So it's very simple, right? So it is the amount of heat, right? Basically, when you see that the delta T is 1, or when the mass is 1 gram, or when the number of moles is 1 mole, right? So and on these conditions, I'll be able to easily get that Q is equal to C, right? So we defined it in this way. It is the amount of heat required to raise the temperature of 1 gram or 1 mole of a substance by 1 degree Celsius. Right? I want to increase the temperature of that particular 1 gram or 1 mole of a substance by 1 degree Celsius. What is the amount of heat which is required is what is called as your heat capacity. Right? And right, this heat capacity is actually going to depend on what is the conditions under which I'm going to do the process, right? So I told you that there are going to be 2 conditions. One, when I have constant pressure conditions, The other when I have something called as constant volume conditions. So at that time, definitely the heat capacity's value will be different, right? So I'm going to give different names to them. So one is what is called as heat capacity at constant pressure, and I represent it with Cp, C subscript T. And then we went on to see at constant volume, it is going to be called as what is that heat capacity at constant volume, and it is going to be represented as Cv. Okay, so these are all the things we saw last class. Correct, right? So we'll move on. We'll speak more about this heat capacity. Okay, fine. Okay, I'm going to give you a situation now, right? So the situation is, say I have, some x, some y, and some z. See, please understand that your heat capacity value is going to be different for different materials. Say for hydrogen gas, it will be something. For oxygen gas, it will be something else. So it is definitely going to depend upon the Cp and Cv values, definitely, right? The Cp and Cv values are going to be dependent on what kind of substance I have in the picture, right? Okay, so if I have three substances X, Y, and Z, right, and I say that X has has a heat capacity, so 5 joule per Kelvin. It can be either in terms of mass or it can be in terms of number of moles. So I'm just telling joule per Kelvin, but you should have either joule per Kelvin per kilogram or you should have joule per Kelvin per mole. Okay, so I'm just giving you in terms without the amount. So say it's 5, 10, and 15. Okay, right. Now if I ask you, right, if I ask you which is a better, okay, arrange them in the order of heat conductivities. Okay, I'm asking you to arrange X, Y, Z in the order of heat conductivities. Now what is given to you are heat capacity values. Okay, now you take some time, take a minute and think and tell me what will be the order of heat conductivities. Go by the definition. Did you understand my question? Okay, hope you understood my question. I'm asking, I've given you the heat capacity values of three substances. I'm asking you to arrange them in the order of heat conductivities. Think and tell me.
So the order I think will be XYZ.
Which is greatest?
X has the greatest.
X has the greatest heat conductivity. Okay, fine. Correct. Why do you say that?
Because heat capacity is amount of heat required to raise temperature by 1 degree Celsius. So it takes least amount of heat to increase.
Exactly. Right. So people, we defined heat capacity as the amount of heat required to raise the temperature by 1 degree Celsius. Right. So what do I understand from this? So for X, if I want to raise the temperature by 1 degree Celsius, I require only 5 joules of heat. Right. But for Y, if I want to raise the temperature by 1 degree Celsius, I have to give 10 joules of heat, and in this case, I have to give 15 joules of heat. So definitely, with the least amount of energy absorbed, wherever I'm going to see the temperature rise happening by 1 degree Celsius, that is going to have the highest heat conductivity. Right. So what I can understand from this is that the heat capacity is going to be inversely proportional to the heat conductivity, or I can say heat sensitivity, or however you want to call it. Heat sensitive in the sense how sensitive it is to heat, how like sensitive in the sense for small amount of heat given, there are going to be large amount of changes in the temperature. Okay, so this data you have to understand, right? Heat capacity is going to be inversely proportional to the heat conductivities or heat sensitivity of a particular substance, right? So in this case, definitely this would have been the order of heat conductivity. Okay, everybody understood, right? Cool. So that is one thing I want to say. Right now, people, right, we'll move on to the microscopic scale. See, please understand, thermodynamics is basically a macroscopic, in the sense, macroscopic uh, study which we do, right? Macroscopic in the sense the bulk phenomena, right? So, but when I go for your, say, your molecular velocities, all the other things, right? All these are microscopic properties. Say the atomic radius, right? All these things are microscopic properties. But with the help of heat capacity, I'll be able to connect, right? I'll be able to connect the macroscopic properties with the microscopic properties, and we'll see how. Okay, fine. We'll move on. Right. So people, right. So when I go into, say, I have a gas, for example, right. So I know that the there are going to be millions and millions of gas molecules in a particular amount of mass of the, or number of moles of that particular gas, right. So these millions and millions of particles will be actually undergoing some motions, right. They'll not be, I know, we studied in kinetic theory of gases, they are not going to be at rest, right. They're going to be constantly moving, right. So this movements which I'm speaking about, right, there can be only three types of motions or three kinds of movements, right. So those three can either be a translatory motion. We know what is translatory motion, straight line motion, right. So that is translatory motion. Or I can have rotatory motion. I know what is rotation, right? Like going in circles, right? That is rotatory motion. Or the third kind of motions I can have is my vibration motion. What is vibration motion? It is going to stay there, but it is just going to vibrate like this. Okay. So these three are the types of motions, right, which I can see, or combination of all these three is what I can see in a molecule. And like I cannot say that this molecule will undergo translatory motion only, this molecule will only undergo rotation. No, it's not like that. Randomly they will be associated, right? So any molecule can take any of this, right? Okay. Now, right now, if I'm going to give some amount of heat, okay, say I initially it is some other molecules are at some 25 degrees Celsius, okay, so I'm going to give some amount of heat to the system, to the gas, right. So what do you think will happen? Definitely all these motions will increase, isn't it, right? The amount of translated rotation, vibrational motion will keep on increasing as the amount of heat I supply is going to keep on increasing, right? Okay, now, right now please understand people, right. If you want to realize, if you want to understand, okay, first thing what you have to understand is, right, the amount of motions, right, the amount of motions is going to be directly proportional to the heat capacities, right. The amount, like say if a molecule has only translatory motion, right, and say there is one other molecule which has all the three, okay. So please understand that the molecule which has all the three types of motion will have higher heat capacity, okay. The molecule which is going to have all the three types of motions is going to have a higher heat capacity when compared to a molecule which is going to have only one of these, okay. So that statement also you have to understand, the amount of motions, right, amount of movements is going to be directly proportional to the heat capacity values. Okay, now, sir, how do I decide? How will I know whether that particular molecule will have only one type, or whether either that molecule will have all the three, or only two of them will be there? How will I understand? Okay, now we are going to restrict our discussion to gases only. Okay, we are not going to talk, we are not going to see much about solids and liquids, right? We are going to restrict our discussion to only gases. Okay, so depending on the atomicity of the gas, we know what is atomicity of a gas, right? So for example, neon, argon, helium, all these are monoatomic gases. So the atomicity is one, right? Because there is going to be only one atom present in a molecule. I cannot call it as a molecule. In the gas, it is going to be in the form of only atoms, right? Say helium, neon, argon, all these things are gases which are monoatomic, right? And I can have something like diatomic gases, like say H2, N2, O2. All these are diatomic gases, right? So depending on what is the atomicity of a gas, I'll be able to decide what kind of motions they can undergo, right? So please understand, people, when I have monoatomic gases, when I have monoatomic gases, right? Please understand that they can have only one type of motion, and that is my translatory motion, right? So obviously, right, if I want to undergo rotation, it is going to be with respect to something else. Okay, so when I have to undergo rotation, it has to be with respect to something else. It has to go around something, right? So if I have only one atom, right, it is not possible for the atom to undergo rotations. Okay, so whenever you have only what is that monatomic gases, I can have only translatory motion present. Okay, now when I have more than one, say I have diatomic, I have triatomic or polyatomic gases, all these things can have all the other three, right? All three types of motions are possible. Okay, because you can understand, right? Vibration motion again is going to be with respect to something else, right? So what I'm trying to say you is, if I have this hydrogen atom, right? So how do you think vibration is going to happen? It is going to happen like this. Okay, hope you understand what I'm trying to tell you. Okay, that is how vibrations will happen, right? So definitely, if I have monoatomic gases, only translatory motions are possible, right? And when I have polyatomic gases, other than monoatomic gases, all the three are possible. But again, just because they are diatomic, I cannot say that it is going to be all the three will be there. Say sometimes only translatory and rotatory motions will be there. Sometimes all the three can be there. Okay, but when I'm going to have a monoatomic gas, for sure I can tell that only translatory motion is possible. That we can say. Understood? Right. So people, right? So this CV value, I mean not CV or CP, the heat capacity value, I told you that it is going to be dependent on the amount of motion which the gas molecule or any molecule can undertake, right? So definitely, what do you think? When I have monoatomic, diatomic, or polyatomic gases, which do you think will have the highest heat capacity?
Polyatomic, sir.
Definitely, right? So polyatom, I told you, right? So whenever you have polyatom, more and more is the atomicity, right? More and more is the atomicity, more and more will be the amount of motions which the molecule can take, right? So, and I told you amount of motion is directly proportional to the heat capacity. And since polyatomic gases can have more amount of motion, so they will have the highest heat capacity values, and monoatomic gases will have the least heat capacity values. Okay, right. So, okay, have you ever heard this term, degrees of freedom?
Yes.
Okay, at least the word, the phrase, will at least you should have heard about it, right? So, degrees of freedom in the sense, what are all the ways in which it can move, right? Okay, so this I'll be actually able to calculate the heat capacity value if I know whether it is going to have only translatory motion, or whether it is going to have translatory and rotatory motion, or whether I'm going to have all the three. Depending on these conditions, I'll be able to actually calculate, right, what will be the heat capacity values of that particular thing, right? So we'll see how are we going to go about it. Okay, so till now, any questions, people? Any questions? Okay, I assume that there are no questions. So we'll move on. So please understand, right? So when I have translatory motion, right? When I have translatory motion, the CV value, right? The CV value. See, this again, I'm going to directly give you the value, okay? But this again, as is going to depend upon the degrees of freedom and all these stuff. You will be studying about it more in depth in physics, right? So for now, don't worry. You can just know the values, right? When I have translatory motion, I'm going to give you, okay, this is the value of CV which I can have. And obviously, if I know the CV value, I know the CP value also. I told you there is a relationship between CP and CV. CP minus CV is equal to R, universal gas constant, right? So anyways, like we'll see about that later. So what I'm trying to tell you is all these values that I'm going to give are not random values. These are derived values, but you don't have to worry about the derivation. At least for chemistry, you don't have to worry about the derivation because we'll be studying them in physics thermodynamics. Okay, cool. So this translatory motion, if I have translatory motion, the contribution I see, right? When I say fine, so instead of calling it as directly CV, I'll say the contribution to the CV value, right? So obviously, if I have only translatory motion, that is the CV value. But if I have all the three types of motion, you have to sum up all the CV value contributions of CV, and the total value is my overall CV value. Okay, fine. So the contribution of CV by translatory motion will be 0.5 R. Okay, 0.5 R. Again, R is the universal gas constant. Okay, so again, R value will be different for depending on the units, right? So if at all I have joules, I have to use 8.314. If at all it is going to be calories, I have to use the R value as, any idea? If I take energy in terms of calories, what should be the R value? I think I told you this. Anybody remembers? Yes? No? Okay. Right. So I'll give it R values now. So R value would be 8.314 if I'm going to use it in terms of joules, and R value will be 2 if I use in terms of calories. Okay. So these two are mostly the values I'll be using. Other than that, I don't use anything else. Obviously, I use 0.0821, but never in these cases. Never in, like, maybe very rarely you will be using, because we are going to generally deal with energy transitions, right? So mostly 90% you will be using only 8.314 or 2 calories as the value of R. Okay, fine. So the contribution of CV by contribution to CV by the translatory motion is 0.5 R. Okay. Now tell me, what will be the CV value of any monoatomic gas?
0.5 R.
Exactly. Right. So because I told you, when I have a monoatomic gas, only translatory motion are possible. So people, please understand that they will not give you the CV value. Say, I will be using these values for a lot of calculations. Okay, which we'll see later, right? So they will not give you the CV value. They will just say that a monoatomic gas is undergoing something, something, find something, something. That's what they ask, right? So definitely you should understand from the what type of gas you have to predict what will be the CV value. Okay, so they will tell a monoatomic gas is undergoing a process of some, say, heated from 5 joules and it expands, and all these things they will say, right? So for all the calculations, you will be requiring the CV value, and they will not give you directly, right? So you have to know, when I have a monoatomic gas, the CV value is 0.5 R because it is undergoing only translatory motion. Okay, right? So moving on. When I have rotatory motion, right, the contribution would be, is it 0.5 R or 1.5 R? One second. Guys, I'm sorry, it is 1.5 R, not 0.5. For rotatory motion, it is 0.5 R. Okay, so for translatory motion, the contribution is 1.5 R, and for your rotatory motion, it is 0.5 R. Okay, I'm sorry, there's a small change. Right, okay. And when I have vibratory motion, right, the contribution to CV, right, would be R, just 1 R. Okay, so these three things you have to remember. For translatory motion, it is 1.5 R. For rotatory motion, it is 0.5 R. And for vibratory motion, it is R. All these are CV values. Please understand, not CP. Okay, and obviously, if you know the CV value, you know the CP value also. That is understood. Okay, so what you have to understand is, people, is, so when they give you a diatomic gas and they don't tell you anything else, okay, when they give you a diatomic gas, right? So generally we don't take vibratory motion into the picture, right? Again, the question is like this: a diatomic gas undergoes a process, blah 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 blah. All these things they say, right? So you have to understand, or like again, you have to calculate the CV value. Generally, by default, right, we do not take vibratory motion into the picture, right? So we will take translatory motion and rotatory motion. So for a diatomic gas, right, the CV value will be 1.5 plus 0.5, which will be 2R only. Okay, but if it is a polyatomic gas, say for example, they gave you ammonia. Ammonia is a tetraatomic gas, one nitrogen atom and 4 hydrogen atoms. In that case, definitely, so other than for diatomic, if you have a polyatomic gas, that time CV value will be 1.5R plus 0.5R plus R, which will become 3R. Okay, so again, I just concise everything in one this thing. So when I have a monatomic gas, CV value will be 1.5R. If I have a diatomic gas, it is going to be 2R. And if it is going to be other than diatomic, if I have a polyatomic gas, at that time it is going to be 3R. Okay, right? So any doubts till now? Any questions? Okay, I assume that you understood, right? Okay, so definitely you can understand, right? The statement which I told, the amount of motion is going to be directly proportional to the CV value. You can easily understand. More and more is the amount of motion, more and more will be the CV value of the CP value. That statement is understood, right? Okay, now moving on. Right. So people, right? So okay, again I'm going to give a situation, right? Like it's an easy thing to answer. It's not a question. I'll only answer it. But anyways, so I have a monatomic gas, right? And I have a diatomic gas. Cool, right? So if I give some amount of heat, if I give some amount of heat to both of them, right? I obviously know that the temperature increase, right? The temperature increase would be higher in same amount of heat if I give 10 joules, 10 joules. If I give, where will I see more amount of temperature change? What happened? Did you understand my question?
Could you repeat?
Exactly. So I have a monatomic gas. I have a diatomic gas. Okay. So I'm giving for both of them, I'm giving 10 joules of heat to both of them. Right. Where will I see more temperature change?
Monatomic.
Exactly. Right. So for monatomic gas, you see that there is more increase in temperature. Okay. Now, people, it is not only based on the CV value, there is some other reason to this also. Okay. So the reason is, right, so when I give some amount of heat, okay, when I give some amount of heat, and if I have only translatory motion, okay, if I give some amount of heat and assume that it is a monatomic gas, we know only translatory motion is possible, right? So the entire energy given to the system or entire energy given to the gas is going to increase the amount of translatory motion only, right? Okay. Now, if I say assume that I have a polyatomic gas where all the three motions are possible, right? So the amount of heat given, some amount of heat is going to increase the translatory motion, some amount of energy is going to increase the vibratory motion, and some amount of heat is going to increase the rotatory motion, right? Everybody understood? Again, I repeat, if I have a monatomic gas, all the energy given is going to increase only the translatory motion. Yes. And if I have a polyatomic gas, since all the three types of motions are possible, say out of 10 joules, 5 joules are going to be used to increase the translatory motion. Say 2 joules of heat is going, or 3 joules of heat is going to be used to increase the rotatory motion, and 2 joules of heat will be used to increase the vibratory motion. Yes. Okay. Now we understood we are giving 10 joules to both of them, right? But the temperature increase is going to be maximum in case of your monatomic gas, right? It is because I'm going to give you a statement. Change in temperature, right? change in temperature is possible and only possible if I have change in translatory motion, right? So please analyze the statement once. Okay, so I'm telling I can have change in temperature only if the amount of translatory motion changes. Okay, so what about the other two, right? So if I give some amount of heat, if at all the three things are possible, definitely all the three motions will increase, no doubt about it, right? But the other two increase in motion are not going to contribute to the increase in temperature. That, or in other words, rotatory motion and vibratory motion has nothing to do with the temperature increase. Please get that to your head, right? Only translatory motion decides the temperature. Okay, only translatory motion decides the temperature. The other two are not going, has nothing to do with temperature. Or the overall energy will increase, definitely. All the three, overall energy will increase, but the energy increase due to translatory motion is only responsible for the increase in temperature. Is that okay? Right? You want me to repeat again what I said? I'll repeat. So only translatory motion is responsible for increase in temperature or decrease in temperature for that matter. Even though I'm going to have change in the amount of motion for vibrational and rotatory motion, I am not going to have any change in temperature. Is that understood? Right. So going back to your previous case, right? I gave 10 joules of heat to both of them. That is a monatomic gas and the polyatomic gas, right? So what happened in monatomic gas? The entire 10 joules of heat is used to increase the amount of translatory motion, right? So, and thus now we told more and more is the change in the amount of translatory motion, more and more will be the increase in temperature. So entire 10 joules is used for increasing the translatory motion, or in other words, entire 10 joules is used for increasing the temperature. That is why you see more temperature increase. But in a polyatomic gas, yes, there is some amount of energy used for increasing the translatory motion, and all the other energy is used for increasing the rotational and vibrational motion, right? But you saw that the temperature is little less increased is because the amount of translatory motion increase in the first case and the amount of translatory motion in the second case it is having a lesser increase in translatory motion. So that is why you see that there is a lesser temperature increase in the temperature. Any questions? Anybody has any doubt with the statement which I told now? Please ask. I know it is little there and there difficult. The best efforts make you understand. But if at all you are not understanding, I'll be happy to tell you again. Is there anybody who didn't understand?
Can you give an example?
I can give you example. Why not? So any monatomic gas and diatomic gas you take. Okay. Say the same example I can give you. So I have hydrogen. I have say helium, right? And say I have ammonia. Okay, right? So I have given 10 joules and 10 joules to both of them, right? So let me give you some random numbers. Okay, so because of 10 joules in helium, I will see that the temperature increase would be say 2 degrees Celsius rise is happening. Okay, but here what I saw is that I have only say 0.5 degrees Celsius rise because of the amount of heat energy given to it, right? Now why is it happening? Is it because the entire 10 joules is given to the translatory motion, right? And I just told you change in temperature will happen only if I have change in translatory motion. The other two has nothing to do with the what is that? The increase in temperature, right? So the entire 10 joules is given to translatory motion, but here some of the energy is given to translational, some of the energy is given to rotational, some of the energy is given to vibrational energy, and only this is going to be responsible for this, but entire this thing is going to be responsible for higher increase in temperature.
Understood,
Yes?
sir.
Yes. Okay. Everybody, please give me yes, people. Everybody understood?
Yes, sir.
Others?
Yes, sir.
Quickly, everybody.
Yes, sir.
Yes, sir.
Okay. Okay. Right. So everybody understood whatever is happening here. Cool. Right. So we'll move on. Now we understood how and all this heat capacity and temperature along with the types of motion, how they are all interconnected, right? See, questions might come from this, question might not come from this, but the understanding this is very little conceptually very important for your knowledge is definitely important, right? So I don't think your teachers will tell you all this. Even in physics, I don't think teachers will tell you all this, but you have to know all these things. Okay, it's a normal thing, right? So obviously, when I this I can see in reality itself. If I have a helium gas, if I have ammonia gas, I get same amount of heat. But why do I see that there is higher increase in temperature, and here why do I see lesser increase in temperature? It's not normal things which you have to know at this level. Okay, good. So moving on. Okay, so again talking. What is the time? We have time. So talking more about this motions. Okay, so obviously all of these three types of motions will have some kinetic energy associated with them, is it not? So since because we're talking about movement, right? So I will have some kinetic energy related to translatory motion, some kinetic energy due to rotational, and some kinetic energy due to vibrational motions, right? And other than that, I can have so many other potential energies also due to some other interactions that will not go in depth because that is out of the scope of your 11th, right? So the thing is if I sum up all the kinetic energies and sum up all the potential energies, basically sum of all the energies, sum of all the kinetic energy plus the sum of all the potential energy I'm going to take. Okay, now I'm going to introduce you to a new term, right? So the term is what is called as internal energy, right? Internal energy of a system. It is not, so in your book they would have represented by the letter of U, right? Or I will be representing it with E because that is what I have been doing for so much long time, right? So in your book they will represent this internal energy as U, and we will be representing this internal energy as E. Okay, but anyways, it means the same, right? So what I'm trying to tell you is what is this internal energy, right? So this internal energy is nothing but the sum of kinetic energy due to translational plus sum of plus kinetic energy due to rotational plus kinetic energy due to vibrational motion plus the total potential energy. Sum of all these things put together of a gas or a system is what is called as internal energy of the system. Okay, is what is called as internal energy of the system. So how will you define internal energy of a system? It is the sum of the kinetic energies due to translational, vibrational, rotational, plus the total potential energy of the system. The sum of all them together is what is called as your internal energy. Okay, so this internal energy, sir, will I be able to know the internal energy value? The absolute internal energy value, will I be able to understand? The answer is no. Why? Because you will have millions and millions of molecules present, and all of them will undergo either rotation or translation. First, I have to find what kind of motions they're undergoing. Even though if I find out what kind of motion they're undergoing, I have to calculate the kinetic energy associated with them. Impossible, right? So what we can do is I will be able to talk about change in internal energy. Delta E, I will be able to calculate. Okay, delta E, I'll be able to calculate. The change in internal energy, I'll be able to calculate. Okay, now next question is, sir, how will I be able to first of all change the internal energy of the system? Now, just now we saw when I give some amount of heat, definitely all the kinetic energy values will increase, right? The translational motion will increase, rotational motion will increase, vibrational motion will increase, right? So one way of increasing or decreasing the amount of internal energy would be to give some heat or to lose some heat to the surroundings, right? That is one of the way, right? So definitely it is going to be dependent on Q, the amount of heat you supply, or say the amount of heat which is lost. So if at all a system loses heat, at that time definitely all this kinetic energy value will decrease. In that case again delta E would be negative because it is decreasing. But when internal energy is increasing, at that time delta E is positive. Understood? Right. Okay. Now this is one of the ways, right? By what is that? Connecting by increasing the, or decreasing the amount of heat energy given to the system. That is one of the ways, right? There is one more way of doing it. Okay. Now one more way of doing it is, for you to understand, let me take a case. Okay, say I have a piston and I have a gas. Okay, right. So what I'm doing is I'm going to compress the gas. Okay, I'm going to compress the gas. Say assume that the piston is here now. Okay, right. I'm telling you, right, there will be a change in internal energy. Right. Now, how do you explain that? When I go for compression, or say when I go for expansion, whatever it is, of a gas, right, there will be change in internal energy. Now, how do you give explanation to this? Any guesses, any wild, whatever you think you can tell me. It's all discussions here. Nobody is going to judge you for your wrong answers.
So it could be because the space for the particles to move becomes less.
Exactly, that's the reason, right? So obviously, initially I had more space for the molecules to move, so definitely they will move at different speeds or different kinetic energies. Obviously, we know what is the kinetic energy. This thing half mv squared. Obviously, for translatory motion. For other motions, we have different things. You will be studying it in rotation mechanics. Have they started rotation mechanics for you in physics?
No, sir.
They didn't start. Okay, so they will start. At that time you will understand all the things about rotatory motion. Vibrational motion you will not study in school. Maybe when you go for college, again specific departments only you'll be studying about vibratory motion. Oh, no, you will be studying about vibratory motions also. You have harmonics, so you will be studying about vibratory motion also in physics in depth, very much in depth you will study. So anyways, what I'm trying to tell you is, so since I have, so initially I had some amount of volume, volume, what is that, was there for the gas to move inside. The space was more, right? So definitely they'll be moving with some velocity, right? Now when I'm going to decrease the amount of space given to the gas, or say when I'm going to decrease the volume of the gas, so definitely the velocities would have changed, and definitely the kinetic energies would have changed, and obviously the internal energy also would have been changed. Okay, now this particular thing, whatever I'm doing here, the expansion or compression, I am going to call it as work. Okay, so I am doing some work on the gas. So please understand, whenever you see, let me put it in this way. Hope you all know, in some advertisement or some form, you should have seen how engines look. Hope you, like, if at all you don't know, so you would have seen something, some piston going up and down. There'll be four, like, say what do you mean by a 4-stroke piston? So 4-stroke piston is basically 1, 2, 3, 4. That is the 4 strokes. Like basically the compression and expansion is what they're talking about, right? So from that particular thing only, the work which is being done there, from that the energy is extracted and the vehicle moves. That's exactly how it is. Again, I don't want to go into the details. So please understand, whenever a gas undergoes compression or an expansion, right, we say that some work is done. Again, the question is who is doing the work, that we'll see later. But For now, please understand that whenever compression of a gas or an expansion of a gas is happening, I would say that some work is done. Okay, right? So here work is done by me because I am compressing the gas. But again, we'll not go into the details, right? For now, please understand that whenever expansion or compression is happening, work is done. Very simple, right? So delta E is going to depend upon the amount of Q, that is the amount of heat given to the system or the amount of Q lost by the system, and it is also going to be dependent on W. W is what? Okay, it is also going to be dependent upon the W, the amount of work done. Again, by the system or on the system. On the system means I'm doing work. By the system means the gas is doing work. So anyways, we will try to understand that later. So for now, what you have to understand is, what is that? The internal energy change can happen by either increasing or decreasing the amount of heat or by doing some work. Again, that's who's doing work, we'll see later. Right. So what you have to understand is this delta E, Q, and W are actually interrelated. Is it not? Now, how will I be able to connect my W with Q? Very simple, right? Say, now in the same case, right? Say, assume that I'm going to give some amount of heat. I'm supplying some heat to this. Okay. Now, what do you think will happen? Now, forget about all these things. Just tell me what will happen to the piston, compression, expansion. What will happen?
Expansion.
Exactly, right? So because I'm giving some amount of heat energy, all the molecules will now move faster. So they will go hit the walls of the piston with higher force. So the piston will move up, meaning that the gas will undergo expansion, right? So obviously the amount of heat given and W are also related, and delta E, Q, W, all these things are interrelated. Okay, so this interrelation, I'm going to give it to you as in the form of a mathematical form, and that is actually going to be the first law of thermodynamics. Okay, actually, before seeing the first law, we have something called, okay, we'll come back to this. We'll come back to the interconnection of all these things in a little while, right? So for now, we will concentrate, like actually, even though if I don't tell you, you will understand. Anyways, so there is something called as zeroth law of thermodynamics. Right? Zeroth law of thermodynamics, and the scientists generally call this law as common sense law. Now, why is it called as common sense law? Is because anybody with little common sense will be able to understand this. That means all of you will be able to understand because all of you are very smart, isn't it? Okay. So what does this law says? Very, very simple. Okay, now before saying this, what this law is, I want you to answer some questions. Okay, say I have two bodies. Okay, I have two bodies, right? So these two bodies, say they are at some temperature T1 and some temperature T2, or I'll call in terms of heat. Say I have some amount of Q1 and Q2. Okay, so assume that Q1 is greater than Q2. That means this is a hotter body, this is a colder body. Okay, now when I bring them in contact, okay, when I bring them in contact, we obviously know that the heat is going to flow from the hotter body to the colder body. Yes, okay, right. Now the question is, until what time the heat will flow? Is it going to be a continuous process? Is it going to keep on flowing? Or is there any restrictions? Until what time or until what conditions will the heat flow from the hotter body to the colder body? What happened? Until what time will they flow? I'm not asking the exact time, 10 seconds, 20 seconds. No. What is the condition on which the heat flow will stop?
Once it reaches maximum melting or boiling point.
Maximum melting or boiling point. I am not even see. I'm not supplying any heat. Right. This some already this has some heat content. This already has some heat content. This is the hotter body. This is the colder body. So I'm making them together. Right. I'm making them touch each other. So definitely heat is going to flow from the hotter body to colder body. So definitely some heat is going to flow. I'm asking. Definitely it is not going to be a continuous process. At some point of time the heat flow should stop. So what is the condition at which the heat flow will stop?
When Q1 is equal to Q2.
Exactly right. So when the amount of heat energy possessed by both of them is going to, and that is the point. So obviously this Q1 will keep on decreasing. This Q2 will keep on increasing because the heat is getting lost by this and heat is getting gained by this. So there will be a point of time when they are in contact, right? Both of them together will have some Q. That means that this will have Q amount of heat and this will have some Q amount of heat. Okay, or if I speak in terms of temperature, say assume that this was a temperature T1, this was a temperature T2, right? So now the again T1 is greater than T2, right? So the heat will move from the hotter body to the colder body. So when will they stop? Is when both of them are at same temperature, or both of them if they have same amount of heat. Very simple, right? Okay. Now this particular condition, when the heat flow is not happening, is what is called as your thermal equilibrium. Okay. So whenever you see that the heat flow has stopped, and when will they stop? When I have same amount of temperature for both the bodies, right? So this condition is what is called as your thermal equilibrium. Okay, so the zeroth law of thermodynamics, or the common sense law, is actually going to be based on this thermal equilibrium, and it's very, very simple, right? So everybody understood at what time the heat flow will stop. The heat flow will stop when the temperature of both the bodies becomes same. So definitely when I compare T1 with T, so T will be lesser. Is it not because some amount of heat is lost by this to this, right? And definitely when I compare T with T2, definitely T is going to be greater than T2 because T2 was very less, right? And it has gained some amount of heat energy. So definitely this temperature would have increased and this temperature would have decreased. And overall, the both of them are going to attain the same temperature at some point of time. And at that point, the heat flow stops, and the condition is what is called as your thermal equilibrium. Okay, right. So very simple. Now we are going to see what is the zeroth law of thermodynamics. Now, since you have understood what you mean by thermal equilibrium, right? So now we can see what is this zeroth law of thermodynamics. We'll see what is that. Right. So say assume that I have three bodies now, say A, B, and C. Okay, right. Now say I am telling that there is no heat flow between A and B. There is no heat flow between A and B. And how else can I call it? If there is no heat flow between A and B means
No
what
Delhi.
can I say? No. Some other thing. Just now we saw what is that. So A and B are in
Thermal not equal thermal
exactly
equilibrium.
correct, right? So if there is no heat flow between A and B, that means A and B are in thermal equilibrium. Okay, right. And I'm saying that between B and C also there is no heat flow. That means B and C are also individually in thermal equilibrium, right? So what can you say about A and C? A and B are in thermal equilibrium. B and C are in thermal equilibrium. So what can you say about A and C?
They are not in thermal equilibrium.
They are not in thermal equilibrium. Why? There is no heat flow between these two.
No, they are
There
in
is no
thermal
heat flow.
equilibrium.
Correct. So that is what is the law, right? The law says if A and B are in individually thermal equilibrium And if B and C are in individually thermal equilibrium, it is understood that between A and C also there is not going to be any heat flow, meaning that A and C are also in thermal equilibrium. As simple as that. Okay. Again, I repeat this. You don't even have to write this statement. You just have to understand that if A and B are in thermal equilibrium and B and C are in thermal equilibrium, it is understood that A and C are also in thermal equilibrium. By thermal equilibrium, I mean there is no heat flow between the bodies. Okay. Any questions? Everybody understood?
Yes, sir.
Yes, sir.
Okay. Cool. So that's about zeroth law of thermodynamics. And I think we'll stop with this for today. So tomorrow's class, we'll be seeing the first law. First law is basically the interconnection of delta E, Q, and W. I'll be giving you an equation, and this is exactly where the actual thermodynamics starts. Right. So till then, it was all about little things which you have to know. Right. So the actual thermodynamics starts from tomorrow. Okay. Cool. Thank you.
Thank you.
Bye
Sir.
bye.
Thank you, sir.
Thank you, sir.
You.
Thank you, sir.